everyone. On behalf of the IEEE student branch of Curtin University Colombo, I would like to warmly welcome all of you to TechXChange, our educational series designed to unite industry experts with curious minds and passionate student innovators. TechXChange is a platform where technology meets conversation, enabling students to learn directly from professionals, researchers, and leaders in the field. My name is Amina, and I'll be your moderator for today's session. It is a privilege to introduce Professor Thrishantha Nanayakkara, the director of the Morph Labs and professor of robotics at Imperial College London. Professor Nanayakkara is a leading expert in embodied intelligence, focusing on how controllable stiffness and physical mechanisms allow robots to perceive and act in dynamic environments. His distinguished career spans world-class institutions, including King's College London, the University of Cambridge, and Harvard University, where he served as a Radcliffe Fellow. A chartered engineer and a senior member of the IEEE, Professor Nanayakkara bridges the gap between theoretical robotics and practical bio-inspired engineering. Please join me in welcoming an innovator who is truly redefining the boundaries of embodied intelligence, Professor Thrishantha Nanayakkara. Without further delay, I would now like to hand over the session to him. The virtual stage is all yours, sir.
Thank you very much, Amina. I'll try to share my screen. Can you see the screen?
Yes, we can see it.
Great. Thank you very much for inviting me for this talk. I'll talk about. Try to minimize. Yeah, so just to give a quick introduction to Imperial Robotics Forum. So we are a community of robotics labs. We have 40 robotics labs at Imperial. And we have 44 principal investigators and more than 100 postdocs and 200 PhD students with about annual average of about 50 million pounds of funding. We have had so far 61 patents and about 16 to 17 commercial spinouts and more than 2,200 publications. So we are organized into home robotics, medical robotics, and infrastructure robotics. This doesn't go away. Okay. So robotics, as you may have heard, in 1980s used to be something like this. These robots used to, fully automated manufacturing plants, but they needed highly calibrated environments, right? So these pieces should come within about 1 millimeter accuracy, and then everything has to be so precise, and then robots are rigid and bulky. And it's quite dangerous to go near these robots, so you don't see humans in these factories, not too many, right? And then, so this kind of environments rapidly changed with the advent of cobots, collaborative robots, in the early 2000s. So a factory with collaborative robots would look like this. Sorry. A factory with collaborative robots would look like this. I don't know why this video is not playing. That's fine. So collaborative robots work side by side humans, right? So like they are safe because their actuators are serial elastic actuators. So for example, this cooker robot and then the person working side by side, and the person doesn't seem to be worried too much about that robot moving around in the background. So the robot has very defined duties like picking and placing heavy objects, and then the worker is focusing on fine handling. So they are safe. Even if you collide with them, it won't do much damage because of this serial elastic actuators in the motors. And then there are many soft robotic companies, like coming from those industrial robots in 1980s to collaborative robots in early 2000s, and then now we are going more towards like soft embodiments in the robots, more and more of that. So you can see like some very famous brands like Festo, Shadow Robot. ABB has some collaborative robots, Empire Robots, and things like that. So what they do is like, so they take like mostly bio inspiration of tentacles and trunks, elephant trunks and chameleon tongues and octopus tentacles or arms, and then make grippers. Mostly soft robots are deployed as grippers in the industry, and some are wearable robots. So because they are very safe to wear. The soft robotics market is growing around 30% compound annual growth rate right now. And it is going to be a very big infrastructure for consumer robots in future. So like we had industrial robots, and we have now consumer robots coming to homes and like anywhere um, near humans. So most of the bio inspiration um, is coming from animals, right? So like you see this elephant. I took this video in Sri Lanka, in I think Yala. No, yeah, uh, um, no, in Vilpata. So there's amazing this, like how they can stiffen some areas of the trunk, and then how they can soften, and how they can like do local control, right? So this is my cat when she was very young, Luna, and then she see how she can kind of almost pour out of a gap in a box. So they can deform their bodies, and they have skeletons, but like they can just deform their bodies and then just pour themselves out of narrow gaps. So these have fascinated the robots. It's like, how do they do that? Like, with skeletons and muscles, and how these muscular skeletal systems have been organized to do that kind of wonderful maneuvers, right? So these things have gone into robotics ideas, and then that is um, uh, that kind of set the stage for software. So I led this initiative with some academics from US to Japan through Europe to write the world's first handbook on soft robotics. So in that handbook on soft robotics, I defined a soft robot as a soft robot is characterized by its capability to generate purposeful structural response when subjected to a specific range of external forces and their associated frequency components, or a combination of both, all with the primary objective of executing a designated task. So what that means is a soft robot doesn't have to be materially soft. It can be a rigid structure, but as far as it exhibits soft features when there are forces and external forces and frequencies. For example, this Toji temple in Japan, Kyoto. I took this photo back in 2000, I think 22. It has several layers, stories in this pagoda. So this pagoda has survived about 400 years of Japanese earthquakes, right? So the secret is that their layers are independent, and then these layers can slide on top of each other. And then there's a slight curvature. It is like, for example, a ball wobbling in a basin. So you can shake the basin and the ball will wobble, but like once you stop shaking the basin, the ball will always stop or settle at the middle of the basin, bottom of the basin. So a similar principle happens here. So when there's an earthquake, these layers start to slide against each other, and then they settle. So basically, it starts to behave like a snake when there's an earthquake. And then this snake-like soft behavior emerges when there's an earthquake. So it was not um, made out of rubber, or it is not made out of any soft material, but it exhibits softness uh, out of rigid components, right? So it is very important to keep in mind that a soft robot doesn't have to be materially soft. As far as it can exhibit softness, it is fine. And then soft robots actually cannot perform without rigid structures, right? So I'll show you in another example where this fingernail is important to feel the touch. So we show with the soft robotic finger that to feel texture, you need this nail as a rigid structure, and then you need this distal phalange bone as a rigid structure to keep the some kind of structural integrity in that fingertip. So basically, the nail is working like a lens, a tactile lens that focuses strain vectors into a very local region to improve entropy of information. So the thing to keep in mind is like soft robots don't have to be rubber. They can be made out of rigid structures, but the mechanisms should be designed so that there is some intelligent autonomous soft response when there are external forces and their frequencies. The softness is always relative to the magnitude of forces and their frequencies. It is not an absolute material softness, right? With that, we can move forward. Um, so my work in robotics started way back in Sri Lanka when I was in Sri Lanka in 2003 after my postdoc at Johns Hopkins. From 2003 to 2006, I worked at University of Moratuwa, and then at the same time, I worked with the Ministry of Defense to develop robots that can detect landmines. Right. So this is me in somewhere above the Punarin Lagoon on the Jaffna side of landmine clearance. So there's somebody looking for landmines, and then me and my students. So we are right next to each other. So I mean, like we were really scared. So we really wanted to get this person out of this dangerous environment and somehow have a robot that are doing that task. So we had this idea of developing the world's first robot that can detect landmines, but this robot is made out of junk. So we purposely designed the robot so that this robot can be made out of rescued or scavenged material from bicycle spare parts and automobile spare parts. So our robots, as none of the components were expensive, and so our motor was a car wiper motor, and then these parts of like all these pieces came from junk material from scrap material. So the vision was to have a robot that can be made in any developing country with landmines, right? So it is you just have to download the design and then go to any junkyard, automobile junkyard or bicycle spare parts shop, and then get the material. All the bearings and everything came from bicycle spare parts. And then at the same time, we trained mongoose to detect explosives, and then we trained mongoose to detect real landmines attached to a robot that could guide the mongoose in the vegetation. So I continued some work when I went to Harvard and MIT, and then there were some commercial activity there. Okay, so but like the problem of that of my experience was that we wanted these robots to be like, very bio-inspired, like walk like reptiles. Like we wanted this robot to walk like a iguana, because the iguanas and reptiles were very in abundance in that area. But our robot was nowhere close to that kind of animals who could have, elegance in that environment. So we were thinking, like, what is missing? Like, so is it about the control theory, or is it about the actuators or sensors or anything? So we soon realized that it is none of that. It is something to do with the embodiment, right? So, and then I thought deeply into that problem, right? So, why our robots are nowhere close to animals, and then why is it? What is the gap, right? So, how can we fill the gap? So, and this is when the first ideas of embodied intelligence came to me. And then I mostly developed those ideas while at MIT, Harvard, and then at Imperial. Uh, when I say intelligence, like, so you always like think about the brain and then synaptic plasticity, or the neural networks in the brain that store information. So these neural networks can readjust or re-network very rapidly, right? So the reason why you can remember what I was talking about a few minutes ago is because your brain can rewire and make new connections so rapidly through synaptic junctions. These synaptic junctions can be remade or relinked in microsecond scale speed, that your brain could remember your brain could make new connections with old memories and anything you knew already about, let's say, landmines, or like anything about the Sri Lankan war. These new networks could basically project their accents, or make new connections with those memories, and then make a new memory on top of that about this robot, so that it can happen that fast. So that kind of plasticity is really important for us to understand the world, or learn the world, or make new memories. That's really important. So you have about 85 to 100 billion neurons in your brain, and that can readily rewire. But something we largely ignore is the other side of the intelligence, which is physical computers in the body, right? So, for example, this ear is you can hear sound when I'm talking, but this ear is organized as a physical computer to process sound information, right? So when the sound waves come to the ear, and then there's like a funnel-like structure, and then that tries to orient pressure waves and filter them, and then the eardrum, and then the incus, these bones can amplify mechanically, and then vibrate a tapered membrane called the basilar membrane. And then this tapered membrane can localize information like the frequency components um, in different locations. And then those localized information can be picked up by the cochlear hair, and then inform the auditory cortex of the brain through parallel fibers. So basically, what the basilar membrane does is, like, it is doing something similar to Fourier series calculations. So, but that Fourier series calculations are done as a real-time computer, as and when the sound waves come in a physical structure, right? So that the brain cannot do. So if the brain were to get your pressure waves directly to the brain, and then do the Fourier series or frequency component separation, and then understand what things, and it cannot do it real time. So there's very slow in that kind of computations. So this physical computer is helping it. And the eyes are another type of computers, right? So the eyes have pre-processing capability. And when you look at something, the eyes will see that part of the screen very clearly, and then the rest of the background kind of smudged and low resolution. So that we call it foveated vision. So what it does is like, so it tells the brain, okay, process that high resolution part of the information, high resolution part of the image, and then don't worry too much about the low resolution information. So it significantly reduces the burden on the brain or the visual cortex to process visual information, and then leaves those peripheral information to be processed whenever needed. Like, so it does like give information such as vectors of movement, and then this, let's say somebody's moving in the background, then that that information is a differential information is good enough for the brain to saccade the eyes. Like, so the brain can ask the ocular motor cortex to control the eyes to saccade, or like orient the eyes towards that moving object and then see if it is relevant or interesting. So but the robots usually don't do that, right? So the robots get very high resolution cameras and then feed our algorithms with high resolution images, and then the algorithms don't know what is important, what is not important, and it does process all the information, which is really inefficient way of computing. And then all the bones and all the joints in our body are also computers. They process a lot of information before it goes to the brain. And then this musculoskeletal structures, they appear to be just like bones and muscles, but they are computers, right? So for example, this knee joint has an angle dependent damper, which is like, for example, by just co-contracting the antagonistic muscles, and then by changing the angle of the knee joint, it can move the cutoff frequency of a low pass filter, and that allows the brain to filter out a lot of information before it comes to the brain, right? And then the important thing is the brain is aware of that kind of low pass filters in the knee joint, and then the brain tunes those bodily computational parts like the low pass filters when needed, right? So, for example, if you're riding a bicycle on a bumpy terrain, if you the bumpiness of the terrain is not really needed or relevant information for the brain to ride the bicycle or enjoy riding the bicycle, and the brain then asks or delegates the task of low pass filtering to the knee joint, and then it gets your body to stand up and then ride the bicycle with bent knees, and then your head gets like stabilized information. High frequency information don't come, and then all those high frequency information are filtered out by the knee joint. So this is always, there's a huge collaboration between the synaptic neural networks and the physical networks, physical computers. So this is, we call it synaptic computing and then physical computing. And then they are aware of each other, and then they always work together. The brain tuning these computers when needed, saccading or angle dependent changing, and then orienting the head to listen to various sounds. So the interplay is very important. So this is what I mean by embodied intelligence, right? So going deeper into the principles of embodied intelligence, I defined a new term called ghost circuits in my handbook on soft robotics. You can sure I can download a free copy of that from your university. Um, so uh, the idea of ghost circuits is that, let's, for example, this is a dead fish, right? So this is a dead trout in a tank. But when there is still water, the fish would like float belly up and then do nothing. But when there is a stream of water, we start a stream of water in the tank, and then we have an obstacle to create turbulence, and then suddenly the dead body starts to swim, but swim against the stream of the water. So this is what you see from the top. This is a dead fish. And then, so when there's this stream and vortices, I'm sure you have heard of this one common streets of vortices. When there's a stream of laminar flow and then there's an obstacle. And so what happens is, this seemingly live response of swimming comes naturally when the dead physical body interacts with the turbulent water. So I see this as a Gauss circuit because like the circuit is not seen, but there's a mechanical circuit or a mechanical algorithm running. And then the interesting thing is a part of the program or the mechanical program is in the turbulent water, and then the other part of the program is in the physical body of the fish. And then when these two things come together, they complete the algorithm or the circuit, and then the circuit starts to function. It is ghostly because like you cannot see how it works and all the components, but when they come together, you can see how it works. But when the conditions are not there, they dissolve, right? For example, if the turbulence is not there, the fish would be just like a belly up floating, or if the fish doesn't have the right softness, right? So the if it is like a frozen fish, or right, or too soft or something, or doesn't have the right shape, it'll just float down, and then the circuit won't complete. So a ghost circuit to complete, there should be all the components should kind of match each other, and then each component should be poised to create that bigger ghost circuit, right? And then it is not limited to one fish, and it can be a school of fish, right? So then they be like, this is why the school of fish have their relative positioning all the time, right? So they are tuning their position so that these vortices best match their position. So the first front of fish, they create some vortices, and then that helps the other fronts to harness energy from those vortices and then passively swim, right? And then when the fish is alive, those are the things the fish would do, right? So they would position themselves in the vortex front in the right way, and then they may tune their stiffness of the body to get the maximum energy harvesting done. And then on top of that, they might actually actively swim too, right? So do some swimming action. So, but they are kind of built up on layers, right? So the first they try not to swim, actually. They try to position themselves correctly, and then they try to tune their body correctly so that passive energy harvesting happens. And then on top of that, they can add another effort layer to swim, right? So that way of swimming is very efficient. And then this is the essence of embodied intelligence, right? Um, so we can use that kind of ideas to solve real problems, right? So here, my PhD student Yukun He, he is solving that problem of energy harvesting in a colonoscopic capsule in colon investigation, in colonoscopic surgery, right? So right now the colonoscopes have to be pushed inside the colon, and then that can be really painful. And then a surgeon has to be with the patient all the time. So imagine we had colonoscopic capsules, just like that dead fish who can swim upstream. The capsule can swim against the downward push by the colon, right? So the colon is always trying to have these peristaltic contraction waves to push a food or digested food downwards towards from the cecum to the rectum. But like, can a capsule use the same peristaltic wave to go against it, right? Just like that fish was swimming against the stream of water. So we can do that if we really notice that. Like, so you can have a kirigami structure that can convert the radial forces to propulsion forces, right? So it is just like diverting that force field from radial forces to propulsion forces, just like the fish was doing. And then we notice that so it can divert both ways, right? So if you contract the capsule and then make it hard, it will push the capsule downwards towards the rectum. And then, but if it is soft, it would push against the contraction wave towards the cecum. So this was funded by ARIA, and then we are continuing that work to do some animal testing, and we use these kirigami structures, very carefully calculated mathematics there. So a soft robot doesn't have to be like made out of silicon rubber or anything, right? So it can be made out of kirigami structures or origami structures, or it can be, any kind of hard structures, but fine as far as it can do a meaningful job in, playing with external forces, right? So this is where here we, have a colon simulator, like, so this is a lab made this colon simulator with contraction waves, and then we can test our kirigami capsule in the simulated colon before testing in real animals or humans. So human trials are like way down, maybe 5 years down, but hopefully we will do animal testing this year. And then this is another example. This is a claw and a pad example. So this is, the problem of wheels. Like, so wheels are really efficient in locomotion on flat terrains, but like when there's roughness, wheels are not really efficient, especially on soft terrains. So the question is, can we design a wheel that has the structural intelligence to use a obstacle as a part of a solution to go over the obstacle, right? And then this work is a collaboration with NASA Jet Propulsion Lab, and then you can download the paper and then the YouTube videos from if you search Pat's wheel. So this is how it works. So see this pad and the claw, like, so if you press the pad and then the claw comes out, and then it just uses the obstacle to do that, response, right? So you can see, claw and the pad, and then even if you push the pad down, the claw will come up. So this wheel has paths. We call it a path wheel because it's a passively transformable structure. Has a structural intelligence to give a meaningful response when it encounters an obstacle, right? So rather than seeing the obstacle as a problem, it uses the obstacle's geometry to solve the problem. So this is the essential idea of ghost circuits, right? So we poise the wheel's structure so that it can use these geometric features of sharp edges on the obstacle to cling on to that and then surmount it. So and then we are investigating other animals who does the same thing. So we are fascinated by these mountain goats, and these mountain goats, their hooves are computers, right? So these are supercomputers basically, and then the hoof morphology evolved. So for example, these dams, like this is almost 90 degrees, like they can climb and stay there. So these sharp edges of their hooves, and then the side edge and then the front edge do some edging on those fine, rough features on the surface that we cannot like even see, right? So, and then that is not just that. Like, so we found that their soft ligaments also work like a mechanical circuit that can autonomously respond if it slips. I'll show you some experiments. So the important thing is when you have a hypothesis like that, and then it is coming from our knowledge about neuroscience and embodied intelligence. So we know that if a signal goes to the brain about slippage, it takes at least about 120 milliseconds to reach the cortex. And it takes about 30 or 15 milliseconds to reach the spinal cord, and then through the spinal cord climbing to the cortex, it takes about 100 milliseconds. And then any computing in the brain is about 50 to 100 milliseconds, and it is not really enough to do a quick response. So we suspect that, oh, it should not be the brain that should be doing the trick. It should be outside the brain. So that is, we call it a hypothesis, right? So, but how to test the hypothesis? We have to really go out, right? So out of the lab and then do experiments outdoors. So this is, we tested various designs based on different hypotheses, right? So we hypothesized that, okay, so this sharp edge might be doing the trick because we saw there are sharp edges on the mountain goat hoof. And how about the tip? And how about the ligaments, right? So does the ligament stiffness matter? And then we can create, like, stiff ligaments and soft ligaments, and then test the difference of them. And then maybe we can put springs into those and different types of springs into these joints and then see their role. So we can test one by one, right? So one morphological feature at a time. And then this is like this kind of immediate observations we can see. For example, if you have the compliance in the fetlock joint and the coffin joint, what immediately happens is, like, so when one digit slips, it can independently catch another feature on the rock when the other digit is hooked onto some other feature. So they don't have to be parallel. So they can slide relative to each other and catch different features on the rock. So that increases the chances of survival, right? And then we test it on ice, like mud, and then rocks, and like climb mountains. So these experiments were done in the Peak District in England. Um, and then that kind of insight is like experience, and then feeling our hypothesis is very important to come back to the lab and then think again, right? So like we tested 50 different prototypes, and Chris was a mountain climber, and Shona and then Alok Ranjan came from Pisa, University of Pisa. So it was a fantastic output, and then you can read all the results in the Nature Robotics journal paper that came out a couple of weeks ago. So and then in the lab test, we come back to the lab and then do more controlled experiments. Like, so what you can see is here, like, so see, like if we slip, like we can see that, okay, as far as it doesn't slip, it's okay to have these morphological features that can hook onto the rough surfaces of the rock. But like, how about if it slips, right? And then what we can see is, like, so we can see this, like, if it is a rounded hoof, as what we see in robots today, it'll just slip down, right? And then right, sorry. Um, uh, uh, let me point options. Yeah, so this one it's a cube, and it'll also bounce on the surface and then slip down. Right. So then just having a sharp edge like a box or a cube is not going to help, right? So then there should be something happening in the dynamics within the cube, right? That the cube doesn't have. So in the mountain goat inspired hoof, what happens is when you release it, it slips, and then when it slips, this compliance in the joints work like flapping on the surface, and then that seemed to be stopping the slippage, right? So that's very important. So and then we realize, okay, so the compliance in this ligament is important for dynamic braking, right? So this is somewhat like what is happening on a automobile. When you skid the car, you apply brakes, and then if it still accelerates, then it goes to a computer that kick starts chopping friction called ABS braking, right? And then you cannot have static friction to stop the car. You have to have chopping friction to stop the car. And in the mountain goat hoof, it autonomously happens, right? Without even thinking. Like it doesn't have a brain, it is not controlling anything, there are no sensors there. These are just markers to track their movement. So it's a dynamically intelligent on its own without any interference from the. When we had a physical intelligence layer in these legs, it can simplify that kind of control. So that is what we are trying to do. And then it's very important. Another lesson is like it's very important to collaborate with other research centers, right? So we are not going to do everything on our own. We always collaborate with other centers and then with other capabilities, and then we combine our capabilities with them and then do bigger things together, right? That is something I really encourage you to do. But for that, you have to have something on your own to offer to them. Um, I will go a little bit into more into the future. So the future is about like AI and physical and robots coming together. So right, like like AI has developed so rapidly, generative AI and all that, like with attention and transformers, all that. Like so, the AI has developed a lot, but that AI needs data, and then somebody has to feed the data, right? So it cannot go and collect its own data. So, but when you have physical robots, the physical robots can move around just like animals or humans, and then collect their own data. And then feed to these AI algorithms and then continue to learn. So that's why big companies like OpenAI and 1X, they are joining forces. So a big part of information about intelligence is coming from fingers, right? The touch information, you cannot really encode touch information in documents, right? So it's very difficult. So touch, for example, this robot, like so it gives that force vector when you touch it, and then that kind of touch information really feeds the brain a lot of information daily, right? So a big difference between human brain and then the monkey brain or the apes, other apes, is that the way we touch things, the number of objects we can manipulate are hugely different, right? So monkeys, what they can do with their fingers is very limited because of the morphology of the fingers and the hand and the foldable palm. But we have a slightly different palm and the fingers that made a huge difference in our evolutionary trajectory and then the civilization, right? So, and then we became master tool makers in the jungle, and then we took a separate evolutionary pathway, and then basically we came out of the jungle about 200,000 years ago, and then we made our own civilization. And then we want to make that same thing in robots, and then it is going to happen with a combination of AI, generative AI, and then physical intelligence and soft robots coming together, right? And So the humanoid robotics market is capturing uh, like kind of wildfire, and then the cost of manufacturing a humanoid robot is coming down dramatically. So it used to be like 2010 to 19, it used to be a humanoid robot about like 3 million. It's super expensive. Now it is less than about $20,000, right? So which is the minimum wage of an employee or laborer, right? So just imagine a humanoid robot you can buy below the annual wage of a laborer, uh, and then that means like the payback period can be very short, right? So you invest in a robot, it can do the same job as a laborer, and then get payback, right? Super fast. And then the humans can do better things. So, go to school, get a better education, and then do more creative stuff. So the humanoid robotic market is like capturing mostly in agriculture, healthcare, and elderly care and hospitality and services. And then the business models are mostly service business models, like rather than selling a robot. So the buyer pays per usage, right? So and then it's like if the robot can add value to the buyer, let's say you buy a mortgage robot, right, a humanoid robot, and then you employ that mortgaged robot in a hospital or a hotel, and then you charge the hotel for cleaning the beds or cleaning the toilets, and then you train the robot to clean beds or toilets and clean the room, and then you charge the, let's say, hotel, let's say $20 or $50 per room for 10 minutes of cleaning, and then you pay the mortgage less than that, right? So you make a profit. So in future, people will be really, just like mortgaging houses, and rather than buying cars, they may mortgage or hire purchase or lease these robots, and then employ them in places where they can do better their service, and then make it money, right? So it is creating that new business environment. So we are focusing in my lab, we are focusing predominantly on the fingers, because like we know that that makes the big difference, right? And then my PhD student, Bhavati Sunil Kumar, she is focusing on this kind of fingertip and trying to understand the morphological features in the fingertip that makes a difference in the touch perception. So the hypothesis is the nail matters, right? The curvature of the nail. We have a hypothesis that the strain vectors um, can be focused using this curved shape of the nail. And then how to test that? So you have to have a robotic finger with a nail and without a nail, right? So and then ask the robot to feel a texture and then tell me the difference between the texture. And then we ask a question like, so what does the distal phalange do? And then for to answer that question, you had to have another finger with and without the distal phalange bone, but the nail and the bone together, right? And then what we see is this. So we okay. So to simplify this, so we have three Hall effect sensors, and then that means these three Hall effect sensors and a permanent magnet particle. And then when you rub against the texture, what happens is this permanent magnet particle kind of dances around those three Hall effect sensors, and then you get three channels of information depending on the flux density, right? So touching the Hall effect sensors. And then with these three channels of information, we can calculate a covariance matrix and then look at the eigenvectors. And then the texture specific eigenvector movements can be quantified and compared using the Frobenius distance, right, between two textures. And then what we see for different roughness levels of textures is that when you have a uh, no nail or a bone, like you feel all the textures like all the same, right? Except some rough surfaces, not the fine surface, like physically rough surfaces, right? But when you have a nail, the information begins to differentiate, right? And then when you have a bone, this like this information becomes differentiated very much. And then when you have the nail and the bone, it is even further differentiated. So this shows that these morphological features of hard and soft formations together work like a touch information processing system. So that means like we can predict the difference between a human finger and a monkey finger based by changing this morphological features, the shape of the nail or the keratin and the stiffness of a monkey nail, and then distal phalange bone morphological features. And we can understand using robotics what is the big difference between a monkey and a human, right? So the way they feel information, and then if a human can maybe distinguish between fine textures like 1,000 textures, and the monkey can only do 100 textures, that says that the human brain is more getting more information or more fine information to think and process, and then that drives the evolution of the brain in a different direction. So that is that. And then we Peyu is another PhD student, so he is extending that kind of ideas uh, with this kind of lattice structures, right? So, and then embedded sensors. So the idea is like, so you can have a hybrid neural network, right? So the right now, like you have this like deep neural networks, and you have an image coming in, and then the entire layer has to process that information. So how about if we can get rid of a large number of layers by having a physical layer, right? So that can do the a more complicated computational role at a physical level before it goes to the neural network, right? And then this we show in this paper that we can do it very smoothly, and then you can grasp so many objects with so much stability, um, and without having to have complicated processing, right? It is not much thinking, and the fingers themselves are intelligent enough to do a lot of processing. We had very linear processes at the end, and then we could. So this kind of robots are really needed in like places like Amazon, warehouses, and then lots of food processing places. The last part of my talk, I want to talk on how to translate these fundamental experiments to practice and to commercial outputs, right? Um, so at Imperial, we give a huge priority to these three pillars of education. So one is we want to learn the basic principles already known to mankind, like Newton's laws, and then all this like Schrodinger equations or anything that is known already. We learn that, and then we want to always investigate what is unknown, right? So all these experiments I talked about, we are doing is to discover the unknown, right? So and then that learning the unknown every day and then making discoveries and pushing the frontiers of technology is another part, right? So learning the known, studying the unknown or investigating the unknown, and then once we know something, how to translate that to businesses, right? So that third pillar is also important. So to give you a quick idea, so this is our annual report, 24-25. Per year, we had submitted 124 patents, new patents, and then 97 were successful. And then we had started 71 new companies in 24-25. And then we have created about 5,500 high paid jobs, not low pay jobs, like very high pay jobs. And then industry research, supporting researches this year was about 64 million pounds, and then consultancy income. And then we have a community of investors, a lot of millionaires and billionaires investing in these companies. And then these companies received about 219 million pounds of investment just within this year. So we keep getting about 200 to 300 million pounds, or that is about $400 million per year of investments in our new companies. So you can see in most robotic companies, most companies are startup companies, right? So and then they will be transferred to big companies in future. So mostly happening in Europe, and America, and Asia is China and India, right? So those are the biggest like giants driving robotics technology. And I think Sri Lanka can be part of that. Right. So I'll talk about a couple of companies came out of my lab. So I think just to give you an idea. So this is an idea I had about 8 years ago, how to give a training to medical students. So medical, so this is our collaborator, Simon Lucian. He was a professor, clinical practitioner, and then they use real patients to train medical students to do physical examinations, right? But the problem with that is like you cannot provide diversity of ethnic diversity or gender diversity to medical students that way, right? So like, but we have a robotic patient. You can present different patient culture backgrounds or gender backgrounds, right? So yeah, so what's happening here in this? It used to be sorry. Um, and then you can project different culture, and then you can transform the structure of the face, a skeletal structure, and then make a Caucasian patient or a African patient or Asian patient, and then the importance of that. Sorry, importance of that is so you can now present various scenarios to a medical student, right? And let's say this is a white female, and then next it can be you can suddenly change, and then they can do facial expressions of pain when you are examining the patient, and then you can give a target like, okay, locate the most painful location, and then you can project a black patient or an Asian patient. And then we notice that like so their palpation behaviors are slightly different when you change across different patients. But then we do an intervention. So when they examine, uh, which give a neutral pain expression, and then we come back to the previous block of experiments. And then we show the same type of subjects, uh, black or white or female, male. And I'll fast forward. What we see is like, so in block one, they had huge variability of palpation forces. And then after 1 hour of training with the robotic patient, for the same diversity of cultures and gender, they are more consistent. And then palpation forces went down. And then this increases accuracy of diagnosis of patients when they go. We see it's like, so this is the medical students, the blue, and then they had that, like they have trained to exert some level of force, and then the novices. But the novices started with the low force, and then they realized that, like, okay, they are not feeling anything or pathological features in the body, but they quickly learned to converge to the real medical students who were trained for years. But like this is happening within the 53 trials, which is about 1 hour of training. So that is fast tracking the medical students training. And then we further, so like muscle core contraction patterns. So when the force, median force increases, they relax their muscles over time, right? So within about 21 or 25 trials, they could do a physical examination with a fully relaxed hand. And that is also important. So this now, we did those experiments for 80 years, and then my research assistants, Elise and Rosne, so they pushed the final bit, and now we have a final product. And then we started a new company called EvoTouch. So we will be marketing a animation software and a haptic mouse that can present breathing or multiple pathological conditions in the body. You can just upload a pathological condition, or the teacher can upload the pathological condition and then tune some tissue parameters in the archived object. And then the student can feel that and examine that using our haptic mouse, the patented technology in the haptic mouse, and then they can learn how to examine a real patient, and at the same time the teachers get to see the palpation forces and then the movements and all the data, and then give more quality feedback to the student, right? So this has significantly improved the speed of learning in medical students and the accuracy of examination. That is why we now have a market opportunity to enter the market, right? So that is through Imperial spin-out process. So another company I spun out through my lab is like when I was in Sri Lanka, the Coconut Research Institute came and told me, okay, so there's this big problem with infest attacks or red palm weevil to coconut palms. It's about like coconut is about like 90 now. Worldwide is about $97 billion industry, and in Sri Lanka, the export income this year it grew by about 40% to about $1 billion per annum, but like about 10% to 20% of that crop is wasted due to pest attacks, right? So how to do that? Like, so we developed a sensor that can listen to the tree and then listen to acoustic signatures of insect activity and then detect it. So and then I push this somehow to the end, and then now I have this another company called Permia Sensing. So
comes
I
across
don't
South
know if you
Asia,
can
Sri Lanka,
hear the sound.
northern India, use crops to unseen threats, disease, drought, poor soil health.
Oops.
Every day, farms across South Asia, from Sri Lanka to southern India, use every day, farms across South Asia, from Sri Lanka to southern India, use crops to unseen threats, disease, drought, poor soil health, long before it's visible to the eye. Camera sensing uses drone-based AI to give you a 3x3 view of your farm's health.
So the important thing is we keep a track of the health of each tree, and then give a dashboard to the owners. We color code it so that the owners can immediately see what trees need attention, and then
Farms across South Asia use Pyramid to monitor vast estates and ensure sustainable yield increase at scale.
To support pioneering startups working to build more resilient food systems. In 2024, on the sidelines of the UN General Assembly, we launched our third competition. We received over 1,200 submissions from 113 countries. These applicants went through 3 rounds of rigorous judging by a panel of global experts. In September, we announced the top 10 finalists who offer exciting breakthroughs to produce more food with fewer natural resources. Since then, the finalists have met our global and local partners, developed plans for how to use their share to help reshape our systems. Today, it is my privilege to introduce you to our 10 remarkable finalists. We announce our from the United Kingdom. Bioacoustics storm imaging to monitor palm farms, detect deadly pests like boosting yields and supporting more sustainable palm to support pioneering startups.
okay, so this was the food challenge, food tech challenge, $2 million challenge, and we, out of 1,200 submissions and from 120 countries, we were among the 4 winners globally, win $500,000 of cash award, which is great. And then we are now moving into UAE market and some of the date palms, India, Egypt. And then we have about 26,000 hectares in Sri Lanka. That is making impact out of that kind of census. And then there's another small startup I have with a family thing called Elanga. So we are trying to, we have done a pilot trial in Kathapa to do precision agriculture. So in the Kathapa village, so we go to villages and then they had very primitive ways of doing farming, and then we give microfinancing, so microfinance loans. But there's a condition, so they have to use precision agriculture technologies. So we basically train them to turn the farmers into entrepreneurs with financial training. So we train them to do cash flow analysis, a budget, and then all this financial planning that they didn't do before. And then we train them to use technology, use drip irrigation systems, and then this kind of weed control systems with plastic covers, and then use more automated or machine assisted farming systems that saves a lot of their money, right? So, and then improves their yield. And then we train them with tech and then data. So that has made a huge difference in their income. So sometimes doubling in their income, annual income. And then we do that as a kind of a profit sharing scheme. So what is really important for you is that you have to do actually when you do technology, you have to study principles, basic principles in the university, and at the same time try to investigate what is unknown, and then at the same time use your knowledge and your research to engage people, right? So especially poor people, if you can transform their lives, right? So the people who are at the bottom of the society, mostly affected by, let's say, landmines, or it can be poor farmers. But can you use translate high-tech research to help them and then make a difference in their lives? These can make profit, right? So, and then this can improve their income, their livelihood, and at the same time, you can also make profit, right? So that is basically our imperial approach uh, of making impact. Uh, and then you can see, this is a serious thing as a university for us. And then that is why a big community of investors are kind of foraging around us, because there's so much opportunity if they work with us. So finally, I will stop the talk, and finally, I want to thank my team, the MOF Lab, all my PhD students and master students. So I can take some questions if you have. Yeah, do you, can you hear me? Sure, I think it's still
can you hear me?
Yeah, yeah, I can hear you. Can you hear me?
Professor, yes, sir, yes, sir. I'm Don from currently just finished my PhD from University of West London in the UK, and from Sri Lanka, fellow Sri Lankan like you. And I'm a big follower of you and a very fan of you, because like your research was very, very impacting throughout the line before the core boards came in. You worked with the generic old kind of robotics, and you made a huge difference. And I read some papers of you, and it's immaculate, like how you came through your journey toward academia, and it inspired me a lot throughout my journey. You should tell I just studied cybersecurity in the University of Greenwich, then I finished information security at the University of Surrey, and just finally finished my PhD in UWO. And throughout the journey, I applied for like several competitions in the UK with UKRI. And in Cyber
Okay.
ASAP, we researched on robotic cybersecurity, which actually like how physical robots can be attacked by various threat actors, and how to mitigate them using deep learning. and we had a government grant, and now like I'm trying to build up my own startup, and like we talked with like different investors in UK, but I'm fellow Sri Lankan, and I'm like I know like Sri Lanka is going through a transformation, and I would like to contribute to my country. So that's what I'm trying to find out, like how do you, as a consortium, like to build something in Sri Lanka, in robotics, Sri Lanka is like far behind. And I know in campuses like Mortua, they have like profound individuals that do revolutionary things to robotics. And how do we like basically get in together? And if you have ideas inside the UK, there's so many robotic researchers as well. And like, how do we get together and have a conversation on what domains are we working on? And how do we join if we have like a funding or any kind of incubator program or UK grant coming up, and we can associate a Sri Lankan kind of a university or a tech path or government initiative to go forward and you know, benefit the both country and UK and also other investors around the world.
Yeah, so I think I usually collaborate through Hatch Sri Lanka and Trace Sri Lanka. So they are good partners. So they know a lot of people or investors and good you know, private sector partners in Sri Lanka. So I would encourage you to contact them. And then if you have an idea in UK, you want to work with a Sri Lankan partner. I mean, usually they are a good kind of, you know, incubating hub. I know, like, so those are two. Like Trace is a public-private partnership, and they have really good startup ecosystem. And Hatch is also, I think they are getting support from UK too. I would encourage you to contact them. And I have tried to work through, let's say, government and universities directly. It has not worked well because it's very hard to find a you know, somebody with a balanced way of approaching something, like, you know, solving a real problem using technology. Different people have different, like, very diverse approaches to doing things. But Hatch and Trace are really entrepreneurial. They are very impact oriented, and they are very positive minded and helpful. They helped a lot with Permear sensing in Sri Lanka. So I encourage you to contact them.
Thank you very much, sir. I'll be sending you an email as well, like further explaining
Sure,
what we do.
sure.
And yeah, yeah. Thank you very much, sir. Thank you.
Sure.
Participants, if you have any more questions, you may please use the chat to drop them in.
Yeah, Professor. So, generic question. So, when most undergraduates like start to select their final year project, they are not that sure whether this will be a worthwhile project or how this would affect us. If you were in a place of an undergraduate as of today, how and what would your advice be for someone who's like selecting their final year project, let's say, and knowing that the importance of like uh, eventually turning it into a startup or commercial application, what would your advice be in this kind of a scenario?
In an undergraduate project, I would prioritize things differently from PhD project or master's project or beyond. In an undergraduate project, mostly you're knowledge is limited, and you might want to really, scope it first, right? So something doable and impactful and interesting for you to, really master some skills, develop some skills of hardware fabrication, software development, control, or testing. But to make it interesting, I would encourage you to really go out of the university first, right? So go and talk to or observe some community you want to help, right? So it can be fisheries, it can be farmers, it can be some company or like arts and crafts companies or any, even a big company, right? So go and talk to them, like, what kind of problems you have that, I can work on. So I did this trial with Jaffna University some time back. I spent a week in the Kilinochchi engineering faculty, and I took the students out to meet the local fishermen. And then, like, apparently, like on the surface, they are very mundane things, but like, when you look deeper into it, you have really good technology opportunities, right? For example, drying fish. So they dry fish and like using like maybe sunlight, but there's a brand opportunity there, right? So like Sri Lankan sun-dried fish is a good brand, right? It's a tropical country, sun is there, and then Sri Lankan is an island, a tropical island. And if you can say, okay, so this is Sri Lankan sun-dried tomato or sun-dried fish, and then associate that with Sri Lanka, maybe there's a branding opportunity, right? And then the problem of branding that is like you cannot guarantee quality, right? So if you just sun-dry fish, every day the taste is going to be different because the fish is going to be different, their texture is going to be different because of the sun intensity might be different from day to day. The wind is going to be different, the humidity, wind speed, and everything. So you cannot build a brand like that, right? To build a brand, the quality of the product should be of consistent quality. So this is where technology can come in, right? So you can have this automated, computer controlled, humidity controlled, wind speed controlled, ventilation controlled greenhouses, or it doesn't have to be greenhouses, but like somehow uh, like houses with uh, environmental conditions controlled. And then if you can guarantee that like no matter what day you're buying, your taste will be the same, then you have a brand there, right? So, and then that can be an undergraduate project. So they did that, and then they derived huge satisfaction. And then there were local like toddy manufacturers, right? So this like curd manufacturers. These are like cottage industries, like toddy making or curd making out of their local milk, but solve the problem of quality, right? So the quality and hygiene, that is something they are missing. So if you can say, okay, so if you follow this process, you can consistently make the same quality, and then that way you can, have a premium sales price, uh, and then make better profit, and then have a scalable manufacturing model. That way you can make bigger profit. So undergraduate students can find that kind of opportunities by yourself. For that, you have to really go out and engage the community, and pick whatever is exciting for you, and then come back to the university and tell your professors, okay, I'm excited about this project, I want to try, and then if it works out, that's great. But even if it doesn't work out, you learn so many things, right? So you learn things about engaging public. You understood some community in your country, and then you developed communication skills of collaborating with fishermen, with toddy makers, or like curd makers that you never met before. And then you learn the skills of like converting or translating your technical knowledge, equations, and any technical know-how to solve a problem, right? So solving that problem. that goes on your CV, and then you become more employable, right? So an employer would love to have you because you have made an attempt to solve a real problem, and then your thesis maybe, or your dissertation might be really interesting. Even if your work doesn't work out to be a startup, you become better employable, right? So that way, that's my advice.
Thank you, Prof.
Aditya, you may go ahead and unmute and ask your
Aditya,
Yes, hello, Professor. Good afternoon. First off,
good
like, thank
afternoon.
you for such a fascinating session today. And I was like particularly struck by, how what permeation sensing is doing, and your comments on how like robotics, interact with organic matter. So I have a question which I would like to hear thoughts on it a bit. My question is on rice farming in Sri Lanka. So during rice farming, like weeding, it's one of the most labor-intensive parts of rice farming, since the rice plants and weeds like often grow close together. If you had to use a rigid gripper or something, it might accidentally crush the crop. So so in that case, do you see a path where we can use like soft actuated manipulators in the field uh, to safely handle this type of situation?
Yeah, have you tried it?
No, I haven't tried. This is just something that I like thought of
Yeah,
about
yeah,
now.
nice.
So
Yeah, yeah, try. You can try different. First, I would say, like, just go and do it yourself, using your own hands. That is how we start, right? So, and then closely observe how you are doing it, right? What are the problems of handling it with your own fingers and your own hand, and then you can kind of infer things about how the brain is controlling your fingers and things like that. That is when you start to think. Right? Abstract thinking doesn't work. So, like, you have to really experience it first yourself, and then come back to the lab and think about it. So I showed you how I started that landmine thing, right?
yes.
So, like, we went to the minefield and then felt fear ourselves, and then it works in your mind, and it makes you a better researcher. Okay, and then try
Right.
out like anything, like, just prototypes. It doesn't have to be prototypes. Like, so you can do prototypes. Have you heard of prototypes? Prototypes are like, things that you can make out of paper, and like, just origami, kirigami is fine. And then you don't have to have motors. You don't have to have complicated actuators. You can move it with your hands and then see how this gripper works, right? And will it work? Can I improve it? And then you do lots of prototyping before doing prototyping. Uh, like, and then you test the prototype. Right? So it's a series of experiments, and then finally it will work out. Right?
Right, Professor. Thank you, Raj.
Yeah.
Are there any other
Any?
participants who would like to share their questions? So, since there's no other questions, we're planning to wrap up now. And we'd like to take a moment to thank everyone who was involved in making this event a success. So, first and most importantly, of course, to our esteemed speaker. Our heartfelt thanks goes out to you, sir, for sharing your valuable knowledge and insights with us. Your session has truly broadened our perspectives and has inspired us to think beyond conventional boundaries. We would like to present this token of appreciation to you to convey our gratitude for your dedication towards being engaging with the student community.
Thank you. Thank you very much.
To the organizing team, the
Yeah,
backbone
thank
of the
you very
event.
much for organizing.
To the organizing team, the backbone of the event. Your dedication and teamwork made this event what it was today, and all of the hard work that you do behind the scenes does not go unnoticed. Finally, to all the participants, we'd like to thank all of you for joining. for your active involvement and enthusiasm. Your engagement truly makes a difference and has driven the success of TechXChange. On behalf of the IEEE student branch at Curtin University, Colombo, we are sincerely thankful to each and every one of you all for contributing towards the success of today's episode. Looking forward to seeing all of you again in upcoming events as we continue to keep growing and innovating. Thank you once again and have a good day.
Thank you. Bye bye. And keep working. Keep trying.